Welcome to Lecture 6. Today we'll be covering the calculus variations part 3. And we'll continue the coverage of chapter 4 of my book. And today we'll be covering constraints, and I'll also give examples. We'll start with the hanging chain and geodesics. But before we do that, I want to recap what we're trying to accomplish with calculus variations. And calculus variations will become crucial in the understanding of approximation theories and the derivation of new structural theories that will be used to understand structural behaviors. But more importantly, when we use approximation theory is the basis of finite elements. So to recap, what we talked about was having a function y of x, which is a function of x, and say I have 2 points for which we would like to find the curve that describes the minimum distance between these 2 points A and B. And we know the answer is a straight line. But if we didn't know that the answer was a straight line, then perhaps it's a different curve, and that curve could look like this. And what we're trying to do is to determine that this is, in fact, we're trying to find what that curve is, y of x. So say we know what it is. What we're looking for then is examining a family of curves, y of x, in the vicinity of y of x. And so what we did, we called this height here epsilon eta x. And we said that that height is the difference between the virtual function y of x minus yx equals epsilon eta x, where eta, epsilon is a scalar quantity, and infinitesimal, and eta x is a smooth continuous function that's arbitrary. We also have that this is the virtual function and y of x here is the actual solution. And so we took that information and then we called this also the del of y. And del of y is really the height difference between this point and that point, which is also equal to epsilon eta x. And so what we're trying to do is, given the functional I, which is a function of y of x, and we'll have integral form, and it could be a function of multiple of y prime, y double prime, and so forth. We're trying to find y of x that minimizes or maximizes I. So what function y causes this to be the case? So that's what we want to do. And to accomplish that, we're trying to find the first version of I equals to 0, which is the derivative of I tilde respect to epsilon. Epsilon equals 0 times epsilon, this equals to 0. And in reality, what we're trying to do there is when we do this derivative, what we're replacing y with y tilde, which is y of x plus epsilon eta x. So anywhere where I have y, I have replaced it with y. And then I take the derivative of epsilon. Respect to epsilon equal 0 times epsilon, set that equal to 0. And then that will allow us to arrive to the Euler-Lagrange equation that when solved that when solved for y, extremizes I of y. So there's a function y that in this case for the straight line minimizes I. And any other curve, I will be larger. But the one that causes I to be the smallest is a straight line for this particular example. So we also covered the example of a beam. In the example of a beam, we know how the beam bends when it's clamped on the left-hand side. And the important thing there is that in that example, I gave you the potential energy, which we'll be deriving, but finding the function W that minimizes the potential energy corresponds to a system in equilibrium. And we will get to that later, but that's just kind of heads up where this is going. But first, I want you to understand the fundamental concepts of calculus variations. So we could examine the example of a hanging chain. And for the hanging chain, I want to bring to attention that there is a particular shape that the hanging chain can take. And we're interested in finding that shape. And so say that I want to calculate the potential energy of this curve, of this hanging chain. The potential energy of this hanging chain F, which depends on X, can be simply be found as the integral of a delta mass. So I have amount mass dm times the gravity, so mg times h. You've heard of potential energy is basically mgh. You've seen this before, but here dm is a small amount of mass here, and so therefore I have dm gy instead, and y here is a height. You may have seen the potential energy of as h before, but I'm using y for the height y of x. And here we will notice then that I have the integral, and dm is basically the density. So I have really rho g y, and then the square root of y 1 plus y prime squared, and then dx. Okay, so that's the potential energy of this hanging chain, and that's starting from this point here, x1, to a point here, x2. So x1 to x2. And the way this came about is that g and y are these two right here, and dm is really the density times ds, this curve ds. So this is ds, and so that really gives you the potential energy for this system. And mass is really rho times d volume. So dm is rho times d volume. I've ignored the cross-sectional area of this chain. We could include it. But what we've done is basically rho A and then ds. And we know what ds is. ds is, and we derived it earlier in time. So ds is square root dx squared plus dy squared. And so when you factor out dx, you get 1 plus y prime squared dx. And so I can plug in ds here, and you see that I didn't put a here, but I can put a there. It's just I'm making it per the cross-sectional area, basically, which is totally acceptable to do. It's just a different approach of approaching it. And so you can also notice that this hanging chain has a given length. And I'll call that given length j of y, and that length is known. Okay, so 0 to L, say, or x1 to x2 if you like. And the length of this change is square root of 1 plus y prime squared dx. And this works out because this is the length of the change really ds, so that's equal to that. And then what I really have is that the potential energy needs to, we want to minimize the potential energy, minimize the potential energy subject to the constraint that the length of the curve is known and given. For that reason, now what I can do is to form and augment this functional. And so I'm going to call this functional f star, and it will be f plus lambda times j. So these are augment the functional with a Lagrange multiplier lambda. And so that's what we got. And so so I'll multiply this term right here times lambda, add it to this one, and then I'll factor out 1 plus y prime squared since it's on both sides, on both terms, and we can just go from there. And so when I do that, I get f star is equal to f plus lambda j, and so that's really the integral from x1 to x2, and I'll substitute f and j, and you can see 1 plus y prime squared can be factored out, so I get basically whatever f is, which I know is this terms right here, rho g y plus lambda, which is this right here, which got multiplied with j. So this is what I got, and this is times dx. So what I want to do now is minimize, render f star stationary, and so to do that, I need to find the first variation of f star and set that equal to 0. In other words, I'm trying to find the function y that minimizes or maximizes f star. In this case, I'm going to try to render it stationary. It may not be a minimum or maximum, but it needs to be rendered stationary. And so to do that, I need to find the first variation of f star, and I will notice here that this integral or integrand big F depends on y, y prime, and lambda. And I'll take the first variation knowing that. So the first variation of f star from x1 to x2 is the derivative of f respect to y del y plus the derivative of f respect to y prime del y prime. And I'll ignore the lambda term because usually when you do that term, you basically get the constraint equation. So it's not really necessary to rederive that knowing that that's going to happen. And so once you get to this point, you set this equal to 0. And this is fairly easy to evaluate. And I'll do it very quickly. Integral from x1 to x2. And I'll first take the derivative with respect to y, which is simply rho g 1 plus y prime squared, and then dash times del y. And then I have the term which is the derivative with respect to y prime. And so for that term, I get rho g y plus lambda. And now the derivative of that is 1/2 1 plus y prime squared to the minus 1/2 times 2y prime and then del y prime. So that's what we get very simply. These two cancels out, and now I'm ready to is equal to 0. So first we have the x for sure. And now what I have to do is integrate this by parts. And to do that will be a little bit of work, but very doable. So let's take this term here. And when you integrate this by parts, you get on the left side, you have rho gy plus lambda. And then this is divided by square root of 1 plus y prime squared with a y prime here, with a del y prime here. And what I've done is I've basically rearranged all their terms in a nice way. You can see that happening right there. So all these terms have been accounted for very nicely, and we're in good shape. And so now I'll integrate first del y. And now the prime is applied to everything here. And this right here goes back into the integral. Okay, that goes back into the integral with the other terms. So, and I won't cover the boundary terms because the boundary terms, let me cover the boundary terms quickly so you can see what happens. The boundary terms vanish. And they vanish because, let's call this A for a second. So the boundary terms are A times del y at x1 and x2, and that's also need to be 0. But y is known and specified at the boundaries. And so for that reason, del y must be equal to 0 at x1 and x2. So this vanishes, the boundary term vanishes. The only thing that remains is what's inside the integral. So I get integral from x1 to x2. And you can see here that I have rho g 1 plus y prime squared square root. And the del y will factor out. So I have the minus of rho gy plus lambda y prime 1 plus y prime squared. And then this whole thing prime del y equals 0. And by the fundamental lemma of calculus of variations, and I am missing a dx, so I should write down the dx. By the fundamental lemma of calculus variations for any del y, this term here has to be equal to 0. And that's your Euler-Lagrange equation. And it can be solved. You can solve for the Euler-Lagrange equation using the code. For example, you could use Mathematica to solve it. And when you solve it, you'll be able to find that the shape of the curve is quite simple to find. When you solve for that differential equation, what you really get is that yx will be equal to a constant times the cosh function x minus another constant. So let's call this constant C1 and C2. Divided by C1 plus lambda, and you have two boundary conditions. And a Lagrange and the length of the chain, which can be used to solve for the shape yx fully. So that's how you approach a problem for that one. Now let's look at the example of geodesics. And what geodesics is, say I'm in LA and I want to travel to London. And I want to find the shortest path. I mean, basically the least time to go from this point to this point. But I have to do it on the surface, right? I cannot go through Earth. I have to go on the atmosphere from this point to this point, right? And so I want to find what the curve looks like. And when you do this, you will find that that curve that goes from here to here is provided by the great circle, meaning this curve will then belong, this plane that connects these two cities, is that plane has to pass through the origin. And so wherever that plane intersects the sphere is how you determine those that shortest path. And so what I want to look at is what is the minimum distance between these two cities, and one way to approach it is by studying and finding the minimum distance. One way to do that is to find a parametric curve and that parametric curve, as you can see, this is in space. So I could say that the parametric curve is given by xt, yt, and zt. Secondly, what I want to do is minimize the distance. And what I notice is the minimum distance can be given by a function like this. The time derivative squared, like that. And that's definitely a distance because you can see that occurring. For example, these are velocities. That's a velocity term. So that's v dt, and v dt is dx. So clearly, this will give you the minimum distance. Looking at this, this is exactly what we need for what we're trying to do. And I want to make sure it's subject to being on the surface of a sphere. And notice here that the functions that I'm looking at is x, y, and z. I'm trying to find x, y, and z that minimizes j, right? And I want to make sure they're subject to the sphere, to being on the sphere. So that means that it's x squared plus y squared plus z squared equals a squared, which is the equation of a sphere. So that whatever function I find has to satisfy this equation somehow. So then I can then construct a augment. I can augment a functional and I'll have j plus lambda times the constraint, call it c. Let's call this constraint c. So constraint c. And so then j becomes, is exactly what I had before, but I'll rewrite it. And I apologize for that. And so that's what I get so far. And then I'll have plus lambda t times x squared plus y squared plus z squared minus a squared. So that is my j star now. So that's my new j star. One thing that's convenient is to put this into the integral, and it doesn't hurt. And that makes things a little bit easier down the road. This is totally acceptable. We can do that, no problem. And so what I'm going to do is now render the function j star stationary. And that will allow me to find x, y, and z to render j stationary subject to the constraint c. Well, in this case, I should, if I want to just write a c, I should just make this equal to 0, and then I can say c. And so now I'm ready now to take the first version j, and notice that the functions now are x, y, and z. So those are the functions of interest. I could have used index notation, so everything's a little bit quicker to write. And I think it is convenient, and I'll just do that quickly if you don't mind. I'll change x to x1, y to x2, and z to x3, and that'll give you practice on how to do that. So this j equals, and this j star, t1 to t2, okay? And now the square root is x, and all I have to do now, because it's index notation, makes everything a little bit easier. Square root of xk dot xk. And since k is repeated, you basically get this term exactly how I have it. And so then I can also write minus lambda. And now again, this is very easy to write. If I were to write an index notation, is easy. So I'll call a different variable, xj minus a squared dt. And now it's easier to take the first variation because index notation makes everything simpler. I also want you to notice how I put a. A is the radius of that Earth in this case. Obviously, if it's a sphere, that's a question of the sphere. So the first version is j star. And I will not do the one for lambda because that automatically renders. I mean, I could do it if you want. Let's call this f. And what I notice is that f depends on xk dot and xj. So f, derivative of f respect to, and let me call it m, del xm, plus derivative of f respect to xn dot del xn dot, and let's do lambda also, so you can see what happens. It usually renders the constraint itself. So let's do the one for the, so let's do this one. So derivative of f respect to xm. So that renders minus lambda. And then I have xj, derivative of xj respect to xm. And minus a squared, that doesn't do anything. Derivative of that is not rendering anything. That's 0. And then I have plus derivative of xj with respect to xm times xj. And I'm using different variables so I don't confuse it with the variables I'm already using above, and that's just done for being careful. But I don't have to be too careful. Del Jm, and that's del Jm. You can see how j and j repeats. You can collapse it. And I taught you that already. So if I have a ij del j, you can cancel j, right? That's one way to do it. Sorry. Let me repeat that again. If I have ai ij, I can cancel I and bring j over. And so this will be aj. So that's what I've taught before, and I can apply those principles here as well. So this becomes xm, and this is here is xm. So I get two of them. And I can continue with the derivation. So now I'm going to go with this term now. And so you can see here quickly that I have a chain rule differentiation that needs to be taken care of. So I have plus, and then derivative is 1/2 xk dot to the minus 1/2. And now I have the derivative of what's inside, which is a product rule. And so then I have the derivative of xk dot with respect to xn dot times xa dot plus xk dot derivative of xa dot with respect to xn dot. And then I have this term, so this del xn dot, and here notice how this is del kn, del kn, and then again this becomes x dot n, and this becomes x dot n. So I have two of them, and the two cancels out clearly. And then I finally have the, and so this whole thing becomes 2xn dot n. And so then I finally have also the Lagrange multiplier here, which just gives me simply, when I do that, I get minus xj minus s squared del lambda. And the whole thing here is in a mega parenthesis dt equals 0. And so then for any del lambda, and then I do have to integrate by parts to get rid of this dot. And so I should probably do that first so you can see what happens. So that's integral parts. And this term doesn't have to be integral parts. And by the way, this becomes simply 2xm. So let's integral parts this term, which looks complicated, but it's not very difficult to integral parts. So these 2 and 2 cancels out. So I'm just simplifying a little bit so that things look simpler. But I think we're ready to integral parts. So I have xn dot times xk dot to the minus 1/2. So simply that, and then del xn dot, and I'll remove that dot, so that becomes del xn, and then this becomes a time derivative here. Plus minus, and I'll not examine the boundary terms. I don't want to do that right now, but by the fundamental, for any del xn, and for any del lambda, what I really get then is minus 2, and perhaps what we need to do is a little bit more work, and I think it's worth doing it. Let's put it back into the integral so you can see how everything comes together. So I have the integral t1 to t2, and I'll just write everything out so you can see what it looks like. Minus 2xm lambda, and that's minus right there, but I also have another minus, so that's going to give me minus d dt x dot n xk dot to the minus 1/2, and then I have the Lagrange multiplier, which I already know what it looks like. And then so one more thing that's worth doing is that this one right here, and I forgot several things here, which is important for me to write. So this is del xm, and this is del xn, and that came from here. And this one came from the previous page. You can see that there. And so I kind of forgot to write here del xm. So I do have to factor out del xm from here, which is the reason I wanted to repeat these steps. And this gives me Kronecker delta in this particular term. Besides factor del xm out. And now this n and n cancel, so I bring m over. So then now I can invoke by the fundamental lemma of calculus of variations for any del lambda and any del x. Then for del lambda, I get the original constraint and then for del x, and then so you can see here del xm. So that's 3 equations, by the way, del xm. I get minus 2 xm lambda minus xm times xk dot minus 1/2 and d dt on that. I apologize. And so m is a free index, so there's really 3 equations there. 3 equations there. I want to go ahead and expand this. I want to expand this. So there's 3 equations there, but that's the advantage of using index notation. It makes everything so much simpler to read. But I have minus, and I'll take the derivative of that. So that's x dot m. So there is a dot here that I forgot. So I need to put that there back in here. I forgot about that. So that's double dot. And you can see here that becomes a square root beneath. And then I can do this, the next derivative, because that's a product rule. So I have minus x dot m, and then the time derivative what's there, which is minus 1/2 times xk dot to the minus 3/2 times the derivative of what's inside. So that's a product rule again. So that's xk double dot xk plus xk, and there's a dot, xk dot xk double dot. So hopefully you can see all that happening. And this is equal to 0. Okay. And so I want to write it one more time, and I will leave it there. And you can see here that there's two of this, really. So 2 xk double dot xk. So these two and these two cancel. And now you have a plus here. And the plus there is coming from this minus and this minus. So then I have the following. I have plus x m dot actually it's better to write it this way. And no negative there. And so that's what we get. It looks like a complicated equation, but it is actually quite easy to solve. When you solve for this, what you'll find, and you can use mathematics for this, but what you'll find is that you'll find the solution to this equation. The solution to this equation is actually quite simple. The solution to this equation you'll find is going to be ax plus by plus cz equals 0, or ax1 plus bx2 plus cx3 equals 0, which is a plane that goes right through the center, and when it intersects the sphere, in its essence, we're talking about a circle, because when a plane cuts through the sphere and it goes to the origin, it basically cuts and forms a circle with radius a. And so that plane is given by this. And these constants a, b, and c can be found because I know what these 2 points are. And so, and you know the radius, which is a. And in essence, that is how you find what that plane is. And so the answer is the great circle. And if you were to plug this into this equation, you'll be able to, I mean, basically this equation is satisfied fully. So yeah, that's a geodesic problem that's of quite interest, and I thought it'd be great to go through that so you can see how that works. I want to revisit the 3D problem I covered in a previous YouTube video, some of you were asking me how to approach how I did the first version of I for the 3D problem because I didn't go through all the steps. But I think what I'll do, I'll cover that now. This is the I function I provided, which is depends on W1. Sorry about that. It depends on three functions and depends spatially on three scalar quantities. And the function that was given is that, and then again, just to be more complete, we can say that W1, W2, W3 depend on X1, X2, and X3 for clarity. And then this is equal to the integral over the volume. And I provided this 1/2 A Wi comma I Wk comma K plus 1/2 Wi d volume minus the integral over the surface, and the surface given was S1b Wk ds. And if you have the volume of material, what we're saying is that on part, and let's say this part of the volume, the surface, that part of the surface, I'll call it S2, and here W1, W2, and W3 are specified. On the rest of the surface, S1, we are going to leave it alone. We're going to say that this is what's given. And so what I want to do is find W1, W2, and W3 that minimize I. And I did forget the BK here. Okay, so that was a problem statement at the beginning as it was given. And the one thing I want to point out is that I and K are repeated. So these are a scalar, and K is repeated, so that's a scalar. But I have to find W1, W2, and W3, so I should get three ordered Lagrange equations for sure. But I start with scalars, and that's okay. And I did write in the previous video this out. I wrote it out so you can see what it looks like. And I want to show you how to go about finding the first version of I. So if I call this whole thing F, I find the first version of I and set it equal to 0. The first step is to really recognize what F depends on. And I notice that F depends on functions like W1, W2, W3, and it depends on W1, 1, W2, 2, and so forth. And so then I have to take the derivative of F with respect to, say, Wm, del Wm. Because this is W1, W2, W3, so F depends on W1, W2, W3, so that this is correct. This is how you take the variation. And so plus the derivative of F with respect to, and what I'll do is choose two new variables that are not used before. I didn't use J anywhere, so I'll say Wj comma P was not used, del Wj comma P, and that'll be it. And then I also had to find the first variation of what's in there. And that's simply, let me call this integrand G, not to confuse it with anything else. And so G depends just on WK. So I'll say the derivative of G with respect to WQ, say, del WQ. And now I'll set that equal to 0, and then I can then operate in go about business. So let's now find this. Let's go ahead and expand. So I have the integral. I apologize for that. Let's work on this term first. I see here that nothing here is Wm, not here. Only here. This term has just Wi. So this is going to survive. So that's going to be 1/2 the derivative of wi respect to wm times wm plus wm I derivative of wi respect to wm del wm. So that's what I get. And then I'll do this term right there. So that's, again, plus 1/2. And now I have, and then I have this a, which I can factor out as well. And then get the derivative I comma I respect to j comma p and times wk comma k plus wi comma I, the derivative of wk comma k wj comma p, and then del wj comma p, and then, and let me clean this up. So this surface is 1, and then I'll then operate, and this over the volume. So I forget to put volume here. And then I have the term over there here, derivative of g respect to wq, which is basically minus integral s1, and that's bk times the derivative of wk respect to wq del wq ds. So sorry for making it messy, but I think we're getting there. So this right here is the Kronecker delta, and I and M cancel out, so the I collapses there. This is also del IM. This right here is a more complicated Kronecker delta, but nothing too fancy. Wij, Wip, and this one here is wkj, wkp, and this right here is del kq. And so now I can operate. Let me bring everything here so we can start clean. And I have the integral over the volume. And I'll just collapse this because we know how to do that. And the 2 cancel out. So I have 2 of them. And that's basically going to give me let me write it out so we can see what it looks like. 1/2 del IM WM del WM I made a mistake here. So this should be WI. You can see that because of this. So I need to clean that up. So the I and I collapse. So this should be I. And I notice that because M should not be repeated 3 times. So let me clean that up. See, this I and I cancel out. So this whole thing really becomes WM. And this whole thing becomes WM because I and I cancel out and M collapses. So I have 2. So I can just go ahead and write out what it looks like. Integral volume, the 1/2 and 2 of these guys cancel out. So I get WM del WM. I apologize for that. And then here, what I need to notice is that this I and this I collapse. So I get del JP. And this K and K collapse also, and I get del JP. And furthermore, so now I'll continue multiplying everything. I think it's worth now transferring stuff here so you can see what's going on. Del JP. And I'll bring the del WP comma Q. And I want to do that from here. Del J comma P. And I think it's worth bringing that over. And I invite you to pause the video and look at this. But for now, just pause it now. Look at what I have. Write it down. But for now, I'll bring this over here for convenience. And then I have the WK comma K plus, and then I have the WI comma I. The del JP is there, and then I have the del WJ comma P. And the volume closes there. And then I have the surface integral, which I found to be minus. And then this K and K collapse, so the Q comes over. And so I really have BQ del WQ ds equals 0. And so now we can do some collapsing here. For example, I have this term, and this JMP and JP there repeat. The process is cancel P out, bring the other J over. And so I really have plus A half del WJ comma J, WK comma K plus WI comma I. And again, I can now cancel P and bring J over. So I get what? I get del WJ comma J. And we can just repeat everything here for convenience. And you look at my here, this summation over J and summation over K, summation over I and summation over K. So in reality, these are dummy indices, and in reality it's really twice of the WK comma K del, and I can just say del WI comma I. And the two cancel out, and I'm really left with this. And now I have to remove this comma I by integrating by parts, which I did in the previous lecture. This is exactly what I got in the previous lecture. I just skipped a couple of steps, and a lot of you asked me to kind of go over that so that you better understood what I had done, which is what I've done this so you can better understand it. But if for the sake of completeness, let me show you how to integrate parts. So these can be integrated parts. So A WK comma K del WI comma I. And since it's the volume integration of parts means it's a surface now. And so A WK comma K, I want to remove this I. And so I get this comma I del WI plus NI, because the volume, when I integrate by parts of volume, the surface is the boundary. And so that surface requires a definition for the normal. So that's why I have to write the NI there. Plus, minus. And that's the only thing that needs to be integral parts. So then I get integral volume WM del WM minus AW K comma K comma I del WI, and this inside the volume. And I have the boundary term, which is here. You can see it there. And that's plus AWK comma K and I positive. And that's the integral over the surface is 1 and times del WI ds plus the integral of the surface 2 AWK comma K NI del WI ds. And then I have this term here that I had not written down, minus S1 BQ del WQ ds, and this whole thing is 0. And so now we can evaluate. So this term goes to 0 because that term, if you recall, I had stated, and I apologize for these marks, apologize for that, but I've stated that on surface S2, W1, W2, W3 specified, and for that reason, this goes to 0 because then del is 0 at the locations where the boundary conditions are specified. So that goes away. But I do have some work to do here, which I want to continue. So let me write in a clean slate what I got: integral volume, Wm, del Wm. Sorry for going back and forth. I hope that you're pausing the video and doing it yourself. It's the best way to learn. When you do it yourself, it's the best way to learn. Okay, this is what we got. What I'm going to do is factor out one of these dels. Get chronicle delta there. This I and I cancel, m comes over. And I'll factor out Wi out of here. Or I could factor Wq out of there. Let's just do that one. Probably simpler. And I do have a mistake because that's del Wi, and what I wrote was Wi only. So that factors out there. And I'm factoring del Q, which means that this becomes chronicle delta IQ. And the I canceled out, the Q comes over. So by the fundamental lemma of calculus variations, the Euler-Lagrange equation becomes Wm minus a Wk comma k comma m equals 0. And note that there's 3 equations here because m is a free index. 3 equations, like I had predicted. We should have 3 equations to solve for W1 in volume V. And the boundary condition simply becomes W1, W2, and W3 specified on S2, while what we found here, and there's definitely a mistake here, minus BQ, BQ equals AWK comma K NQ on surface 1. So not only have the Euler-Lagrange equation, I have the boundary conditions to the problem on the whole surface. So hopefully this clarifies a lot, and this should match what I had in a previous YouTube video, and I hope it's a lot more clear. Let's go back to the hanging chain problem. And I want to cover something very quickly, and it has to do with the Beltrami identity. And I want to show you the usefulness of that identity. Okay. I apologize. And so I don't know if you recall, but we had this. This is very complicated to solve, and you can do it in Mathematica, which is fine, but it can be very cumbersome. And what I want to do is use a different way to solve it, and there is a different way to solve it. So if you recall, you can get the order Lagrange equation to be something like that. So your order Lagrange equation typically ends up like that for a particular set of problems, but usually looks like this at the end, where f sorry about that, where you usually have this situation, and f is a functional too, and depends on y prime. But there are situations where f does not depend on x at all. So there's no x there. So if f does not depend on x, there's a little trick, and the trick is to multiply both sides by y prime. So you multiply this by y prime and this by y prime. Okay, and I'll write it out for you. This is equal to 0. And I'm going to use a chain rule, but invert it. And so let's go ahead and do that. So y prime so you can see here, if I do product rule on this, when you add this to this term, you'll get that term. So it's a little trick, but why don't pause the video? Just take the derivative of this and add it to this, and then you will get this term, guaranteed. So it's a little trick. It's a chain rule inverse, but it is an idea that people have used. Now, so what we will do is a little trick even further. So note, we want to note, and this is all mathematical. I'm not going to ask you to do this. Honestly, if you get to this point, you can run in Mathematica and you will get the shape that we got, which was a cosh function. Cosh. So we got a cosh as a shape of the hanging chain. But what if you want to do it by hand and solve it? I'm showing you a couple of tricks to do it. So that the derivative of f respect to y prime, let's note this for a second, is the derivative of f respect to y respect to x. Okay, and I should not use this. I should use dy dx because that's not a partial. Plus so again, I'm not asking you to memorize this. It's not necessary. This becomes y double prime, or the second derivative of y. And I want you to notice how this is y prime. So this term right here is that term. This term here is that term. So I can write this equation and plug in for this whole thing. I can plug in for this. And so I'll do that. So that's the derivative, and I'll extract d dx f y comma y prime minus y prime df dy prime, and this is equal to 0. You'll see very quickly that what I've done now, I've done something very neat, because now I can integrate these equations on both sides to get just simply f y prime I mean, just f. I mean, I can just write f. F minus y prime df dy prime equals 0. Or a constant, because when I integrate as value of 0, I get a constant. So that's very powerful because now I have simplified this differential equation into this one. So I've gone from something that looks more complicated to something simpler. And so for us, if you recall, f was a much more complex function. And I'll invite you to go back and look, but the function f simply looked like this. F was equal to lambda minus mgy square root of 1 plus y prime squared. That's what we got earlier. So I can plug in what f is into this equation. And when I do, I get lambda minus mgy 1 plus y prime squared minus lambda minus rho gy times y prime squared square root of 1 plus y prime squared. And now this is equal to a constant, which I'll call k. The neat thing about this, I can use Mathematica to quickly solve and show that from here, sorry about that, from here, when I multiply both sides, I multiply this whole thing together, I'll get something much simpler. And it's going to look like this. Y prime squared equals lambda minus mgy divided by k minus 1. And this is squared. So as you can see, it becomes much simpler than what I had before. And all we have to do is solve the simpler differential equation. And if I set my boundaries to be just like for the hanging chain at x equals minus a and x equals a, I set it at y, I set that 0 and I set this at 0. Then I simply will get, with those boundary conditions, I'll simply get y of x equals k over mg using Mathematica, cosh function, mg x over k minus cosh, sorry about that, mga over k. Okay, so it becomes a lot simpler, and you can even solve for k, because k right now is not known. And so we know we can show that y prime of x using this equation here. We can show y prime of x is sinh, the sinh function, mgx over k. And then I will substitute this into my Lagrange multiplier. Okay. And when I do that, my Lagrange multiplier was, if you recall, minus a to a, 1 plus y prime squared dx. Let me make sure I have a prime there, squared dx. And when I plug in what y prime is, okay, when I plug it in, I get that this is 2k over mg sinh mgx over k. And now I can solve, because I know the length of the chain, I can solve for k and then plug it in into the equation for y of x. And so the thing I want to make sure you understand is that I'm not trying necessarily to, it's more mathematical. So So I'm just trying to show you that earlier we got this, and solving this is very hard to do. But you can do it mathematically, get the same answer. But my point is that there is a technique called the Beltrami identity, which basically means that if f does not depend on x, you can jump from this equation to this equation right here. And by using that equation, then things become much simpler to solve. And you can see that we did it here step by step, and we're able to quickly get to the solution. And the hanging chain shape is this one with this k given and can be found using the length of the chain. So I know L and I just need to find K. Okay. So that's how you approach this problem. And I hope you have a great rest of the day. I covered several topics today, but it's supplementary. We need to keep moving along. So hopefully this makes sense. In summary, covered some problems on constraints, and I went over the problem we covered in previous YouTube video more carefully, and then I've also covered the Beltrami identity.